The area under a curve. I feel like that's not.
Differential equation.
Carly, that's fine. No, that's fine. It's not.
Oh, what you guys like?
Say how it's going. Stop.
Like last year, so
Okay, guys, page 13. So today we're talking about something called washer method, where there's a gap or a hollowness to the object that we have to make sure we subtract out so that we can get the true volume of that object. But just to review this method first and just see that connection. This method, we always start off with shading our region. And then we're going to be looking at the axis of revolution. So here, everything so far, your axis of revolution have been flushed up against your shaded region. There is no gap at all between the axis and the shaded region. So the easy way to tell is if your axis is up against the flat surface of your shaded region, you're always going to have, at least for our purposes, you're always going to have just this method. But if your axis of revolution is either up against a curved region, or if it is if there's a complete gap or hole, we have to make sure that we subtract out that hole. Otherwise, we're not getting the true volume of that object. But with this method, we only have to worry about building one radius because we're doing cylindrical discs, and there's no hollowness there. It is just a dense object that we can just find the volume for. So this method is a little bit easier, but washer method requires an additional step. Okay. So if you take a look at this leaf that is, that's pointing in that 45-degree, that kind of at a diagonal way. And let's say we're rotating around the x-axis. So I'm going to put a dotted line there. Now it's touching, right? It is touching the axis, but is it up against the flat surface of the shaded region? It's not, right? There is no flat surface here. So no matter what you do with this shape, it'll always be a hole or a gap. So you see this gap here that was not existing before. So I think some students would think that, oh wait, it's this method, as long as it's touching. That's not true. If it's not up against a flat surface, if you see any sort of a gap or hole, that's enough for us to make sure that we need to subtract something out. So what's going to happen is if we were to take that leaf-shaped region and rotate it around the x-axis, it's going to kind of create this bowl-shaped. You see all that hollowness inside. We got to make sure we subtract all that out. Okay. So if you were to slice this object into infinitely thin surfaces, you're going to be getting this ring-shaped. You guys see that? If you were to cut just a slice this out, you're going to get differently shaped rings, and we're essentially finding the area of those rings and accumulating them over the entirety of our interval. So this could be a two-dimensional version of a slice that we may see when if we're looking at this object. Okay. And if I asked you, how would you find the area of the outer ring? How would you go about doing that?
Total minus white space.
So you would find the area of the larger circle and then do what?
Minus the white space.
Yeah, minus the area of the inner circle, right? So, so the area of that of that shaded region is simply going to be pi big radius squared minus pi little radius squared. Now, would you ever find the radius going between the outer rings? No, right? So we want to make sure that everything that we do with radius includes the center of the object, okay? But this is going to be the potential tendency that we're going to experience is sometimes we may want to connect between the two shaded regions, but that if it doesn't include the dotted line, if it doesn't include your axis of revolution, you're not including the center of your object. So if we were to take this and extend it a little bit further, imagine if I can take the pi out, then I'm left with r squared minus little r squared. And if I were to go through that a little bit more, this represents the area component. I have the dx, which is the width component, and then that leads us to what we call the washer method. Okay. Very similar to this method, it's just that we have to spend time to subtract out the radius of the inner circle. Okay, so pi big R squared minus little r squared. Something we got to make sure that we don't do is we don't do this. We don't do big R minus little r quantity squared. Okay, this is not the same thing. Okay, so we want to make sure that we square our radius separately and then subtract them separately. Just like how if we had a vertical horizontal axis of revolution, we're always going to be doing a vertical radius. If we have vertical radius, things are easier. Top minus bottom, everything's already pretty much ready for us to use. But if we see a vertical axis of revolution, we need to pause for a moment because we know that if we draw a horizontal radius, it'll be right minus left. And most of the time, you're going to spend time to rewrite your equation to get it in that right minus left format. Your equations has to be in the proper form. Your bounds have to be in terms of y. So everything is going to be slightly adjusted, just like how we did with this method. If there's a vertical axis of revolution, just know that we gotta spend time to set things up. Okay, so we're gonna have to draw two radius if we realize this is gonna be a disk method. Washer method. So there's big R. Big R is the distance from your axis of revolution to the outer curve, the curve that's further away. Okay, so axis of revolution is the dotted line. That's the true center of your object, even though the way that we draw our axis of revolution is going to feel like it's at the edge of the diagram, but that's before we rotate, right? Once we rotate, that axis is going to be the center of your diagram, of your object. The distance from the axis of revolution to the inner circle, that's going to help us find the area of the smaller circle, which we're going to subtract out. Okay, so let's look at example one, which is we're going back to this, but we're going to do an example that is for this problem. Example one, find the volume of the solid enclosed by the graph y equals x squared and y equals square root of x revolving about the x-axis. So here's the x-axis. We're rotating around this horizontal line. Even though it's touching, that's not good enough to be this method. It's got to be up against a flat surface. We see there is no flat surface here. There's a gap. If there's a gap, we know that there's going to have to be washer method. So if we were to rotate this around, it'll look something like this, right? It'll be a bowl-shaped object with that inner portion. Now we're going to draw two radius here. One radius is going to extend. So it's always important that we do this, that we start at the dotted line and we extend to the outer boundary. Okay. That's going to be your big R. So start on the dotted line and extend to the closer boundary, that's your little r. As long as your two radius are sitting next to each other, it's gonna be obvious which one is the big R. Big R is gonna be the one that's longer. Now, if you put them far apart, then the graph can suddenly change in a way that little r feels bigger than big R. But if you just make sure that whenever you put them, just put them relatively close to each other, and that way it's visually easy to tell, okay, that's obviously big R, that's little r. Big R is longer than little r. And make sure that you always include your axis of revolution, right? We never want to do this. We never want to draw a rectangle or radius or quote unquote radius between the shaded region, because if it doesn't involve the center, it's not called the radius, right? We're essentially doing this, right? We're connecting between the outer and the inner boundaries of our shaded region, which is not, we can't call that the radius then. Okay, so we'll spend time finding our big R and little r. So big R is just the top minus bottom of our big radius. So the top of big radius is sitting on which curve? The top here. This graph is what? Square root of x, right? Okay, so top minus bottom, square root of x minus what's the bottom of big radius sitting on? 0, minus 0. Now, if we want to find the area, we would do root x minus x squared. Okay, but we're building our radius here, so we're never going to subtract between the two graphs. Okay, little radius, top minus bottom. What's the top of little radius sitting on? X squared. What's the bottom of little radius sitting on? The 0. Okay. Obviously, we can drop the zeros, but I want to just show us that we are actively identifying the top and bottom and subtracting them. Okay. If we were to find the boundaries, we can set the two equations equal to each other, but here it's pretty obvious that my left bound is 0, my right bound is 1. So now it's easy. Now you're just plugging into the formula. Okay. From 0 to 1, everything's in terms of x. Bounds are in terms of x, or expressions are in terms of x. We have to square your big R and little r separately. Do not subtract it first and then square it once. You got to square these separately. Okay, we can put it into our calculator. I'm going to have y1 hold big R. I'll have y2 hold little r. I'll call math 9. Depth integral from 0 to 1. Alpha trace y1. I'm going to square y1 minus alpha trace y2. Square that. Yes. Make sure again that you're squaring your radius separately. 0.3 is same thing as 3 over 10. Make sure we're going to leave pi out of the calculator and just attach it on our own. Okay, any questions? All right, example 2. Find the volume of the solid generated by revolving the function y equals x squared plus 1, bounded by the line y equals 2. So here's our shaded region. And we're going to rotate it about the x-axis. That's going to be our axis of revolution. Okay, so x squared plus 1 is just going to be a parabola that's going to open up with the y-intercept at 1. And then the line y equals 2. So here's my shaded region. But I'm rotating about the line x-axis, y equals 0. All right, is there a need for washer method here? Well, is there a gap between it, or is the axis of revolution up against the flat surface of the shaded region? It's not, right? So what's going to happen now, if the axis was up here, if it was y equals 2, that's perfect, right? Then we can rotate it around. There's no gap. We can just rely on one radius. But here, it's going to be a funny shaped object here. It's going to be a ring shaped object with a curve on the inside. You guys see that? Again, we never have to worry about drawing it. I just want to make sure that we can distinguish enough so that we know, okay, this is this method versus this is washer method. There's a gap here. We need two radius, one radius will extend from the axis of revolution to the outer boundary or to the further boundary. And then from our axis of revolution, we're going to extend to the closer of the two boundaries. There's my big R and little r. Okay, does that make sense? We need the bounds. How do I find the bounds? Set them equal to each other, right? You can also use your calculator and do your intersections between the two graphs if you want. But I'm going to work it up by hand here. That's nice. Nice whole numbers, nice integer values there, 1 and -1. Okay, let's build our big R and little r. Top minus bottom. What's the top of my big radius sitting on? 2. Minus, what's the bottom of my big radius sitting on? The bottom of the big radius. 0, yeah. There we go. Okay, little r. The top of little radius is sitting on
X squared plus 1.
good. Minus, now what's the bottom of the little radius sitting on?
0.
0. That's how we do it. Okay, so wherever your big radius and little radius is sitting on, that's where you're subtracting to get that length. Okay, so now it's easy, right? The hard part is, can you get the intersections? Can you get your little radius? Can you get your big radius? Because after that, as long as you know what the formula is, you're just putting to the formula and making the calculator find the answer for you. And the rest is just calculator work. Okay, the easier ones are always the top minus bottom, but whenever we have right minus left, we got to flip everything around. Our equations have to be rewritten, our bounds have to be readjusted. So let's skip example 3 and let's go to example 4 on page 14. Any questions here? Does anyone have any? Okay. All right, example 4. So we have the same shaded region as example 1, but now rotating about the line x equals -2. So we're going to extend my x-axis. So we're going to rotate this shaded region around this axis. It's going to kind of create kind of a lampshade looking object. Again, we never have to worry about graphing or picturing it too much. We just have to have enough visual connection with it so that we know whether it's this method or washer method. Okay. All right, is this a disk or washer method? Washer, right? There's no flat surface. Even if it was touching, no matter where you have horizontal and vertical lines lined up, there's never going to be any chance this can be anything except washer method. there's always going to be a gap or hole. Okay, so starting on your axis of revolution, this is a true center, right? This is going to kind of flip over and rotate over to the other side. It's going to create, this is the true center of the object here. From here, you're going to extend to the furthest boundary that you can find. That's going to represent your big R. And your little r will extend from your axis of revolution to the closer boundary. Make sure that you always start your radius, start at the center. Okay, I know this looks like the edge of the diagram, but it's really, this is the true center here, because there's this part is also going to show up as well. It's going to create. Now, this is right minus left, so are the equations that we have in front of us suitable here? No, we got to rewrite it, right? So this was y equals x squared. But if I solve for x, I get plus or minus square root of y, but only is only on the first quadrant, so just positive square root of y. This other graph was y equals root x, but if I solve for x, I get x equals y squared. Okay, let's build our radius here. All right, so big R, right minus left. What is the right endpoint of my big radius sitting on? Equals root y, okay. So I start off with root y minus root y minus, what's the left endpoint of my big?
Negative.
Good, so there's two negatives, right? So we gotta make sure we keep track of that. Root y minus a -2. Does that make sense? Okay, little radius. Right minus left, the right endpoint of little radius is sitting on
Y squared.
the y squared. Minus the left endpoint is sitting on the -2. I'm stacking these circular rings from down here all the way up to up here. So what are my bounds going to be?
0.
0 and 1. I know it looks like the same from before, but we're looking at the y values, right? And now it's easy, right? If you can build your radius, if you can get your bounds, then as long as you know what the formula is, you're just inserting into your formula. So the calculator looks like it will not be able to get it down to a nice fractional answer. So you're just going to round to 3 decimal places and then attach pi at the end. You're always using x's in your calculator. So I have y1 holding my big radius. I have y2 holding my little radius. You can probably just pull the previous entry that you had and just adjust the bounds because it's already in that form of y big R squared minus little r squared. Okay, any questions here? Hey, we'll just work through as much as we can between pages 15 and 16. The keys are attached, but go ahead and start page 15. I'll walk around to see how you guys do and if you have any questions for me. Keys attached, so you can always check your progress, but I also want to see if you're comfortable with drawing your radius, identifying is a disc or washer, and then finding your mounts, either by hand or using a pocket to find it. Oh, question. Can't tell if this is this or washer. So you see here's dotted line, right? Oh, so there's a gap like this rotating around this. It will revolve around one percent.
Yeah, but if it's touching, it's not always that way.
Well, it's not touching at all.
Yeah.
So this is gonna be washer method. The only chance that this can ever be this method is if it's revolving around x equals 0 or y equals 1. That's the only way. Any other place, there's no revolve or gap.
Okay, yeah, but like, it's like this lead, it's just like,
Right, you're right. Here, there's no chance for this method. Everything's gonna be washer method here.
okay. Is this like the only exception or?
I think it's harder to create this method than washer method. Because unless there's a flat surface on the shaded region and you're up against that flat surface, it's always gonna be a washer method.
Okay.
If you see a horizontal radius, it'll always be, it's gonna be by minus left. The minus left, your equation has to be as much as x equals. If you see a vertical radius, it'll be top minus bottom, is gonna be just a regular function, so like. Okay, is that from X? That's why. So. So 1A should feel easier because you're doing top minus bottom. There's no need to adjust your equation. We get to part B. There's some additional setup that you have to do. So when you draw the pieces, one will be on the same graph. No, the two boundaries are here, so one will extend to here, the other will extend to. Well, because the shaded region has two boundaries, right? Oh, okay. So you would never use this graph, basically. Right, this will be acting as your boundary. Okay. You're stacking rings of. Okay, so this will be a boundary.
Why can't someone calculator?
I don't. Yeah, sorry.
True.
And so do as much as you can between the two pages. I just want you guys to get as much scenarios as you can, and I think the more you see, the more comfortable you're going to feel. What the intersection you said what you have to do. When it's not obvious when my bounds are. So here, this is pretty obvious. That's gonna be my upper bound. My lower bound is gonna be wherever my graph is going to get the y. That's plug 0 in for x. I should be able to tell that's BS negative. Okay, so negative 1, 2. But if the graph is connecting at a point where it's not obvious where that y value is, then I'll just set the equations equal to each other by that intersection that I'm making. Okay, you're done with page 16, 15, go to page 16.